Mic check. Mic check. Oh good, it's somebody's morning. Okay, looks like mic is working. I need another minute or two just to make sure all my my tech stack is set up okay. I think I got the official Sele working well now. Not really sure what the problem was. I am a glutton for punishment, so I guess I'm coming back for round two.
Oh,
Oh wow, that was really loud. Let me go see if I can
sorry.
turn that down. There we go. Okay, say something now.
This is me talking kind of normally.
How is the volume for everybody in chat? Mossler is on Discord.
Oh, hi, everybody. I didn't realize we were live.
Oh yeah, we're live. I'm still getting ready though. I haven't actually like kicked off the stream yet. Let's see. We can hear you, but is the level of Mossler okay? Oh, it's only 5 concurrent viewers now.
Okay. That makes me slightly less nervous.
Oh, he is a bit loud. Oh, you know what? Can I just change that in Discord? I don't think
Oh,
I
I feel like
can.
I hear myself double on stream.
Oh, you probably can. Here, I gotta find a way of turning you down some. Okay, try now.
This is me talking. Hello.
Is that too quiet now? Maybe here? Try that.
That sounds good to me.
Oh, I just realized I can swap this for here. Okay, what about that? Say something.
This is me again. Hello.
Okay, let's see how people think those volume levels are. That should also make it so you probably can't hear yourself either. Like the double. You can't hear double.
Okay.
Okay, it sounds fine now. Good, good. I think we're gonna start.
So for some reason on
5 minutes.
Discord, you have a very high-pitched screeching noise in your mic.
I guess I'll just turn off Discord so then you should be able to hear me through the normal stream. I just realized.
I can now hear you through the stream, but keep in mind there's like almost a 10-second delay on that, so that's gonna make things kind of awkward.
Okay, then give me a moment. What about this? Is this stream for Discord better? Can you hear me now over Discord?
There was no difference. It's the same.
What about now? Is this good over Discord?
Oh, yes, that's much better.
Okay, excellent. Oh. Okay, so I guess another. I don't really want to like open it up for another like 3 minutes though, and then I'll give the introduction and all.
Okay, while you're doing that, one thing you could consider doing is if you give general people permission to speak in this channel and use voice activity in this channel, but not to join, then you can like drag them in from another voice channel.
How do you do that?
It's just in the permissions on this voice chat here.
Mm-hmm.
And then let me double check real quick. Yeah, so if you go to the permissions and then you just select the @everyone role, you can turn off the view channel and the connect, but you can turn on speak and use voice activity. That way a moderator can manually drag them in and they'll be able to talk, but they can't come in without permission.
I'm first of all going to disable the soundboard.
I thought we disabled that, like, server-wide.
I think that this is correct now. Okay.
Okay. Can't test it, but we'll try it later.
Yeah. There is a Discord channel, Alex. It's in my Discord server, but I'm only inviting specific people to it because my goal is to make sure that all of the conversation remains on topic. It's really hard for people, I think, in general voice channels on Discord to stay on topic. I guess there's really no reason to hold off any longer. We could just go now. It's only 14 people, but it is a weekday, so I don't expect very many people to join. Wait, did I mistype something? Stack. Oh, yeah. That's right. Okay, I guess I'll take this little thing off, and we will get started. All right, everyone, thank you for coming out to the second Let's Write a BitBang USB Stack from Scratch on the CH32V003. This is a little 10-cent microcontroller. It is a lot of fun. It is really, really basic. And my goal is make it so that it can do USB. And the second part of that is a bit of a joke, but to see if I can turn it into something like an Arduino. The first live stream, I hit a lot of snags. I went down a lot of dead ends. I have some better ideas now, and I figured I would just document literally every step of this, including all of the dead ends, and what better way than to do a live stream. So for this particular live stream, we're going to give up on all of the fancy DMA stuff, and we're going to do something a little bit more basic. We're going to fire off a GPIO interrupt, and we're going to rely on instruction timing. I didn't want to do that last time because instruction timing is variable. It can change if the chip is doing a lot of stuff. But we can also retime it. So if we do find that we're falling behind while we're working through USB, we can go try to fix that up. And I plan to give that a shot, but let's just see if we can just do it straight first, and if that works out, at a later point we can try to do the fix up. So that way user code running in Arduino land will be able to work with this. The next one is, we just had a lot of different directions we were going to go last time. I'm just going to try to pare this down a lot, and today my goal is not to start reading USB packets, but today I'm going to try to lay the foundation for us to be able to start reading USB packets. So I'm going to hopefully not bite off too much more than I can chew, because I want this stream to be no more than 5 hours long. So we're going to be just basically going through a bunch of instructions in the interrupt and taking notes and seeing how long everything takes. So the output of today's goal is going to be to take a lot of notes. Now, hopefully this is going to be useful to a lot of other people, because if you ever want to know how long does a series of instructions take, a lot of times to sort of like wrap your head around how fast things are or what operations to take, you just have to have a good idea as to like how many clock cycles everything takes. And so one of the other notes I do want to make is that we're going to be this table will be, and we're going to be running from Flash. Let's copy that. Running from Flash with one wait state, or it's one extra wait state. That's the default for this processor, and we're going to be running at 48 megahertz. My hope is that when we run to the my hope is that when we run from the boot ROM, which is, or boot flash, the boot section, which is 1,920 bytes of flash, that they'll be the same. Never tested that. Maybe it's not, maybe it is. We'll find out at some later point. Who knows? Maybe live stream 10 or whenever we finally get around to it. And so what I'm actually going to do here, and so this is exactly the same code that I left with last time, is I'm going to go just get rid of most of this code, because we're not going to be doing DMA. We're not going to be doing, well, hardly any of the stuff that we were going to shoot for last time. So I'm just going to remove all of that. But we are going to keep the external interrupt handler, and I'm going to keep it in interrupt. So one of the first things we're going to want to do is just start with the basics and say when we're on our system, if we turn off HPE, which we have HPE off, HPE, I don't remember what HPE stands for, but basically it's a mechanism that the processor uses internally to go store a bunch of state really fast before you run your interrupt code, and then when you return from your interrupt, it restores all of that state. The problem is it doesn't save S0 and S1, which I don't know why they didn't do, because those are kind of important things to store the state of. And it also does raise the minimum amount of time that you can go do your thing. Oh, hardware prologue and epilogue. Actually, Sam, I'm going to add you to the permissions for to let you talk. That is if I can figure out how.
He should already have access because he's a moderator.
Oh, okay. Yeah, that's weird. I can't add new people. Oh, wait, here it is. Anyway, so Sam E says that it's hardware prologue and epilogue. He's reading the manual right now on this. So we're going to turn that off because I think that it adds a little bit more of a wild card, and it is a little bit faster, yes, but it would be really cool if we could make this work with the slower one anyway. So we're going to do that, and I'm not going to be doing any timer stuff. So we're going to go get rid of the timer code as well. So we're going to get rid of that. We're going to maintain the external trigger. So we're going to maintain port D3. We're going to tell the USB system that we're going to go on bus, disabling HPE, which I just already talked about. We're going to delete the DMA code. We're going to delete the timer code. We're going to enable the interrupt. And I guess we don't need any of this right now. We can just busy loop real quick. Okay. Let us give this a shot and see if this compiles. So this won't tell us anything, although it compiled and ran, so that's pretty good. But what we're going to do first is we're going to go, hold on here. We're going to go, when we get in the interrupt, we're going to go trigger this high, and we're going to go trigger it back low. So that's port C0. And so what I want to do now is I'm going to just go monitor it. I'm going to unplug and plug in the USB, and we're going to see how well that works. First of all, I notice is that, oh no, here it is. Yeah, that is right. So what we should see is, oh yeah, look at that. So we have our interrupt happening right here, and around here is where our code gets started. So 443 nanoseconds later. That's a while, but that's not insane. And as we use more registers, that's going to go up a little bit too. But that's okay, because when one of the things that we're going to look for is an EOP, that's fine. We're going to hit the EOP, and we're going to be able to be aware that that's what it was, and we're going to be able to trigger off of it. And say we're actually transferring data, it doesn't really matter if we miss even the first 2 bits, 3 bits. What matters is that we're going to be able to hit an edge, time off of that edge, and then go and start our state machine. Because what happens at the beginning of a USB packet is it's going to have something called a preamble, which is 111110. Actually, while we're here, let us turn on the USB protocol decoder. And I think D plus is channel 0. Yes. So this is the sync in the beginning. So, or I guess it's 00000001. And with USB, whenever you have the bit flip from one cycle to the next, that indicates a 0. But if it remains the same, it's a 1. And so what we're going to do is I'm just going to say, I know at some point we're going to come in here, and we're going to then look for the edge, and then we're going to start our state machine. So it's okay if we miss a couple cycles. That's fine. We're just going to see if we can get going. So the first thing I really want to do is I want to go see, can we figure out how much, say, like a NOP is here? Can we measure the difference between there being no NOP here and having a NOP here? So if I say, I always forget if it's ASM volatile or volatile ASM. I use this enough that you would think I should know what it is. But what I'm going to say is NOP. And so we're going to start by measuring this. So it's 62 nanoseconds, 62 nanoseconds, 62 nanoseconds. So it looks like it's around between 60 to 62 nanoseconds. So we're going to say baseline. This part of the test turns a GPIO on, runs some code, and turns it off. And that's going to be 62 nanoseconds. Time.
One cycle at 48 megahertz would be 21 nanoseconds approximately.
Okay. One cycle is 21 nanoseconds. Okay. So our baseline is 62 nanoseconds. So what that means is that it's actually 3 clock cycles for us to write to a GPIO. But we can verify that. So let's first try it with the NOP. So I'm going to go run now, and we're going to go say start. Kind of unplug and replug, and then we're going to go take a gander. So let's zoom in here. So before it was 62 nanoseconds, and now it's 82 nanoseconds, which is exactly one more clock cycle, which is exactly what I was hoping for. Extra, or just one NOP. And what that's going to say is 82 nanoseconds. So one clock cycle is all we need for that. But what if we wanted to do something different? What if we wanted to say output to an IO? So let's output right now just a 0 to the BSHR register, which is going to have no effect whatsoever on the hardware. But it's going to take a little bit of time to execute. So let's go give that a shot.
Real quick, someone's asking where they can get this dev board.
Right now, I've just been mailing them out to people. I don't think there's an official source for this dev board. The other thing to note is until I get USB up and running on it, I'm a little bit nervous to sell it with the USB resistors installed. But if you join my Discord server, you can do it there. And really the way I've been doing it is just any of my patrons. If you're my patron at any level and you ask, I can just mail one out. I did get more boards ordered, so now I have enough for right now. And programmers. So let's see here. An extra operation, though, leads us to 104 nanoseconds. So BSHR set a volatile.
This is a little off topic, but I was curious from the other day. Is there a difference in how long a compressed instruction takes versus how long a regular length instruction takes to execute?
We should find that out today. And actually, instead of writing this in C, let's do this in assembly. And so I have somewhere here, GitHub CNLore assembly cookbook. I never remember the semantics for this, so I always just copy paste. Let's see, let's find a RISC-V one. Wow, I really don't have very many RISC-V examples. Okay, well, whatever. Okay, so let us do this as IO. Also, we should check alignment. That would be a really good one. We should also look up what are the RISC-V ISA or compressed ISA. Actually, RISC-V. What I want to see is which registers we're allowed to use in the compressed set. And that's on here somewhere. So it says we're allowed to use S0, S1, and then A0 through A5. So
yeah, I think it's the lower 16, if I remember correctly.
I don't think so. It looks like it's A8, A9, A10, or X8, X9, X10, X11, X12, X13, X14, and X15. Give me a second. Oh, hold on. Okay. So I'm just going to do A0, A1, and A2, just to be some registers we can use. And so what I'm going to do is I'm going to say, so let's load immediate A0, and let's load 1 into there. And I'm going to go load immediate A1, and we're going to load, well, 0 for right now. And then load immediate A2 and 116. And so what this is going to do is turn it on, we're going to set it, and we're going to turn it back off. So store word, A0, and then that big chonking register. A0, A1, and A2. So if all is well, which it probably isn't, I probably messed something up, this might turn the GPIO on, do something, and turn it back off. So let's take a peek. Zoom out. Looks like this did not work. So the GPIO is not turning on and off. So what did I mess up? If anybody in chat sees how I messed up, please let me know. I'm loading A0 into the register. I'm loading A1 into the register. Oh, I need the address of that. Okay. L value required in assembly statement. What does that mean? Maybe it's not equals R? Oh, that's output. Let's try that. Okay, so now this is working. So let's just make sure, for sanity's sake, that we get the same number. We don't. That's 82 nanoseconds. What we just tested was that that would not be the case. Oh no, just one NOP. But if we store it, it says 104. Okay, let's try swapping this back to a NOP and seeing how long that takes. $60 nanoseconds with a NOP. So that means there is something hokey going on with the C code. We might have to write our front end of this in assembly, which I'm not sure how you guys in chat feel about that, but I mean, I'm willing to do it. I've written a lot of stuff in assembly before. So if this turns into an assembly affair, then that's all right by me. It says 40 nanoseconds. So I'm going to go correct the baseline. Baseline is 40 nanoseconds. Just one NOP is 62, and this was 82 nanoseconds. So let's just stick with assembly for right now, because it seems to actually be, it seems to actually work. So this was just making sure. Baseline is 40. Yeah, it's, I don't know what GCC was doing. So one of the first things that, it was Sam, right? Was that who was asking about the performance difference of compressed versus not compressed?
Yep.
Okay, let's give it a shot. So the first thing we're gonna do is store word A1, 0, and all that jazz. And let's just make sure that we know what we're doing. Oops. And so we're gonna go here. Unplug, replug. Okay, stop. And we're gonna go take a peek. So that's 80 nanoseconds, which is exactly what we thought it would be. So now what I'm gonna do is c.sw, and we're gonna see how long that takes. So let's run this.
Someone in chat thinks you mistyped. You put 62 instead of 82. But also they are very happy about assembly, so I don't think you have anything to be worried about.
82. Got it. Thank you. I've corrected that. Wow, this is actually a lot better than I thought it. Like, I really like doing this with Discord on. So that was 80 nanoseconds. What I'm going to do is I'm going to try to include a c.nop right here. And what that's going to do is it's going to change our instruction alignment. And I want to make sure that if we have different alignment on our instructions, it's still going to operate the same. So let's go peek here. "104 nanoseconds. That's not good. Isn't it? Or is it? C.nop 104. Oh no, that's actually just fine. Nop then c.storeword is 104 nanoseconds. So no, that actually makes sense. So that's fine, I think. I wonder what happens if I do a store word here. Does that wreck anything up? I will show you guys what's actually going on in the underlying assembly in just a moment, why I'm testing both sides of that. But this says 102. So no, I think that this is okay. So a nop then a store word is so 104. Yeah, so nop then, or c.nop. So the reason I was testing that was if I look at the list file, right here, what we have is we have the store word that we wrote, we have a nop, and we have another store word. GCC was clever. These were all compressed instructions all the time. So I'm trying to remember, does anybody in chat know how to force GCC to emit non-compressed instructions?
It's the I believe it's march option.
Oh, but no,
GCC.
I want to use them, but I don't want the I want to. There's like a special syntax. So like c dot operand or c.sw says use the compressed instruction for this. There is some other trick to making it to forcing it. In this case, here's the SW to use the non-compressed version. Let's just try a bunch of things. No, it's not .sw. Full word. Underscore. GCC inline or GCC assembly. Don't use compressed instructions. No, that's not it. N? I'll try N. But that's kind of funny because on Extensa N means narrow, which is basically a synonym for C. Word? I don't know. There might not be a way of doing that, but there is a trick that we can use. What I can do is I can use a register that's not one of them that can be a compressed register. So T0 and T1 are both registers that can't be compressed. And so if we do this here, so T0 and T1, and we put T0 here and T1 here, we can force it to emit non-compressed instructions. So let's take a look. Oh, wait. Okay, well, I'm really confused right now. Maybe there's some special one for compressed stack pointer stores? Anyway, I mean, it kind of does what I want, which is what I'm trying to do is I want to measure how long this takes. So right now, this is at address 17C, which is aligned, and 17A is not aligned. And I want to see if, oh yeah, we should make this a full one. So if we, okay. This is going to be annoyingly tricky. T2, T2. So I guess what I should do first is test this and then see what this works out as. Okay, so this would be c.nop, then storeword and ioreg aligned. And that's 104 nanoseconds, or 102, whatever, 102, 104, same difference here. We're talking about clock cycles. And then what happens if I just write this? Is that going to do what I want? No, it's still a compressed instruction. But what we could do is we could put another... Oh, but if we put it before, that would mess us up. No, I really do need...
You use the expansion of the NOP instruction as add I, but with a... can you force the width on the constant for add I?
Does the folks in chat, is he scratchy to people in chat? He's scratchy for me.
Oh, okay.
I'm gonna try muting it for a second. Oh wait, I guess I was supposed to mute me. Oh no, it's just all of my Discord now is scratchy. Okay, well, even if he's scratchy for me, I guess that's fine. That must just be my audio is scratchy. Which, whatever, it's fine. Anyway, we can just do that, and we're just gonna load a worthless... Oh, we can't do 15 though. We could just write to another register, so we could do 1024. Okay. So now, hopefully, our instruction will be unaligned. So right here, 17E, our store word is now unaligned. So let's see if this takes any different amount of time. Oh no, 124 nanoseconds.
Real quick, is there a way that you can maybe trigger on the signal so you don't have to zoom around in here all the time?
I actually have no idea. I don't think there is with the Sele software.
That's unfortunate.
I thought they added triggering, but I haven't used it in a long time.
So that's 124. So that does mean that that's going to be a bit of a road bump for us. That our alignment is going to be that sensitive. I don't know. Can you put alignment statements inside of assembly? Does that work?
There's a suggestion in chat for how to trigger.
You can use with that software the tab below the play button. You choose the channel you want to trigger from and what kind of event to trigger on. Okay, I will give that a shot in a moment. So let's go back to here. 176, 17A, 17E. It clearly is possible to align. So if I say align 4 here, I wonder what happens. Also, I do want to see this, so I don't know what you're referring to. You can, with that software, it should be in the tab below the play button. Well, that's a little weird, but okay, sure. I'm not sure why aligning is inserting so many NOPs. I still want GCC in general to use compressed instructions. I just meant when I'm writing the compressed instructions in my code, I want it to not mess with my alignment by changing the width of its instructions.
It might be beneficial for just our testing if we want to switch over to not using compressed instructions. At least just one time, and then we can switch back and do the switch to see what happens.
I think this is actually sufficient as is, though. I'm able to test all of it. I can force an alignment at the beginning, and then I can just manually look at the code and see how it's all set up. It is unfortunate that that is so different timing-wise, but let's just take a peek here. Store word, add I, some big chonker, and now we have an unaligned compressed instruction. So my theory is this should be 104. Yes, that's good. Okay. So what we can do is write into here c.nop then SWIO-reg, and this will be C.SWIO-reg unaligned. It's going to be 104 nanoseconds. So that's really reasonable. It's unfortunate that we have to be careful about the alignment of Friday. Let's just take that off of him for a few moments. Friday. Anyway. I can write a .s file and link it in. However, GCC on .s files will still do the weird, wacky, oh, I can compress this instruction. Oh, I can't compress this instruction, and aligning things that way. Also, I like more and more the inline assembly approach. It's just nice to be able to intermix it with C. But that is an interesting point. There are some benefits to writing it as a .s. Let's just give it a shot. I mean, I have 5 hours. My goals here today are pretty clear. I think it'll be okay. Now he's like on the back of my chair. Friday. Can't do that. Hey, no bitey. Okay. Let's give it a shot. Let's go write a .s file. So the instruction, or the symbol that we're overriding is this one. It's going to be a .global, and we're going to totally crib off of their existing code. So what I can do is just copy and paste the GCC code in here, and we can just work from there. So add I SPSP minus 28. Wonder what this is doing. A54011. Is that the address of the of port C? Let's see here. Hold on. Okay. Let's see. So port. So GPIO. Out at VSHRC, register offset, but where's the register core address here? Port 10410. Yeah, okay, that looks like that's what's going on. 10411, 10411, yes. So that's interesting. I wonder if I can do LA, if that will turn into the same code. And I guess the second question is, can I just include fun.h? Pound define assembler. Because then I could say LA A5. What is it?
I have a hunch LA will turn into the exact same code because it's a pseudo instruction.
I think it will too. Okay, so the answer is we're allowed to use this plus, and actually, do we have to? We could just store that as our debug. Ooh, there's another interesting tidbit here. If we don't use port C for our debug, but we use port D for our debug, we only have to use one register to hold both the USB and our debug. Let's do that. Yeah. Define debug 2 pin. Ooh, we should have a header file now. Let's see here. I'm going to leave port C hooked up in the C code, but I am going to tear it out of the rest of the code here. DPU pin. I really don't like how exticr is defined because it's so hard for me to read this. I think Paralyn, I don't publicly say how all that went, but needless to say is, well, I mean, I'll say what I can, which is I'm not allowed to work on it anymore, but for a very good reason. No more, sorry, this is a question about the Vive tracker stuff from chat. I can't work on it anymore. Okay. Let's GPIOD base. Let's just stick with this. Let's at least see what this code looks like when it's compiled and see if it's anything reasonable. Oh, we also have to add it to our makefile. I forgot about that. Let's see, how do we actually add this to the makefile? We're going to go add a .s file. Oh, there are additional C files. That's a weird thing to call it, but I guess that's what I called it. rv32 or rv003 usb.s. And let's give it a shot. Oh boy, oh boy, oh no, so many errors. Okay, well, no time like the present to make it so this is allowed to be able to compile into an assembly file. How hard is this gonna be?
I'm gonna bring Wilmore in here.
Okay, thank you.
Oh, that did not work. Let's try this again.
I think this is going to be reasonable. So what we're going to have is...
Okay, I don't think I can. You might have to do it.
I'll give it a shot. I already added Wilmore to have access. Oh, I think I know why.
I think I just don't have permission to move people.
I'm not sure if that worked. Let's see if that worked. So what I'm doing right now is I'm going to be guarding all of the things which are actually C code and can't be compiled in assembly with poundifdef assembler. And that way, if the assembler sees it, it's not going to try to compile it. It's just gonna be like, oh, I guess that's something different. I can't do that.
Wilmore still cannot join on his own. You should be able to literally click and drag him into here, I think, though.
Give me a moment. I'm going to attempt to edit the category that this is in. Okay, well, I'm about to try something a little bit scary. Okay, I've just given Wilmore permission to the category, but not to admin. When Wilmore gets here, I just want to make sure he can't see the admin channel for our server.
Okay, he's in the other voice channel right now.
See if he can see this one.
Okay, I'll check with him.
Wow, you know, if this was a pound define instead of an enum, it would just work. But nope, people like their enums. This is why I try to avoid enums some of the time, not all the time. But it's just another reason to not absolutely run it. So DIY in the ghetto, the purpose of this is to take this little 10-cent microcontroller right here and give it the ability to talk USB.
Okay, so Wilmore now has access to the admin channel that you did not want to give him access to, but cannot access the voice channel.
Welp. Give me a hot minute.
You should be able to literally just click and drag him out of the other channel into
I mean,
this one.
I know I can, but then I can't, then he can't be part of this normally. Tell you what I'm going to do is I'm just going to create a new category. Also, oh man. Okay, Wilmore, can you get in streaming now? Oh. Apparently it stripped off his permission when I moved it. Okay, now Wilmore should be able to get into this channel. Is that him?
It's me.
Neat.
We got there.
Well, I've probably blown this all to smithereens. Let's see. Oh, well, I guess I didn't blow it all to smithereens. Oh, I do need to show line numbers, though. Why? Wait, am I blind? Oh, I was blind.
First option in display, yeah.
Okay. I guess there's really no reason for this anymore. Oh, I see what that was for. Yeah, that's fine. Yeah, I'll get rid of that. That is fine. Okay. And then it complained about a different line number. It complained about line 3593. Oh. Wait, where did it... Bingo. Wow, that wasn't that bad. Now we can pound include CH32V003 fun in a assembly file. Okay. Let's see here. Line 8. Oh, that wasn't that bad. GPIOD base. So what does it not like about that? What is GPIOD base here? Thank you, Randall Young, for the super chat. I will not be getting pizza tonight, but thank you nonetheless. Oh, dang it. Foiled. If we're an assembler, we can't do this. So an assembler, you can only do that. And then unrecognized opcode ret-i. Oh, it's mret on RISC-V. So compile. Now, it's not going to do anything, but let's at least look at the code to see what that looks like. Oh, this looks wonderful. And Sam E, you were right. In fact, it does LUI A5 0x4011. Give me a second.
I obtained that forbidden knowledge through having to write the TCC RISC-V assembler.
Well, this is starting to look up. I think we can go this route. Okay. So that was fun. So what we're going to want to do is we're going to want to read and write the BSHR register. And BSHR, actually, what is the offset on all of this? Oh, we want D, so 1. No. Oh, no. These are really sparse registers. I was really hoping that we would be able to like store the first part and then be able to use like the other commands to read and write to the other registers in the area. So like for instance, if I could read and write to BSHR here, and I could read and write to INDR here. Oh wait, 1041 408 101410. Oh, maybe it is possible. 4 408 410 CFGLR 400. So what does that actually work out to? That's GPIOD base. Oh, they are all together. Well, that's pretty good. Okay. Yeah, I think that's fine then. It also means we can do things like quickly turn the bus around, and because when we get a USB message, we will have to write back. Okay, so I think that that'll work. And so GPIOD, let's make sure this is right. So GPIOD base 40411. Oh, ADI A5 410. Okay, so it actually is already doing the thing. It does take 2 assembly instructions to actually load that register in. That's fine. Sure. Well, we still need to back up A5 because we didn't do that yet. Store word A50SP. Okay. Let's back up a couple other registers. So A0, A1, A2, A3, A4, A5, A2, A3, A4, A5. And we're going to go load these. So 4, 8, 12, 16, 20. And we're going to go unload them when we're done. So load. Let's actually try. I'm willing to go for the gold. Let's give it a shot. Let's actually try to write out to A5. So load immediate A0 1, or no, what are we doing? We're writing to port 2. So that load immediate A1 2 plus 16, and we're gonna go store word A0. Let's make sure we're actually plugged into PD2, and we are. PD2 is yellow pin in Sele, and we're going to do that 0 of A5, and it's actually not 0. It's going to be a slightly different value. It's going to be 0, 4, 8, 12, 16, if I'm right. And I want to make sure that that fits in the compressed instruction for what we're going to try to do here. So for loads, it's 2 bits and 3 bits, which I think can store a number that's big enough, right? Load word 5, 6, 10, 11, 12. Yes, we can. Also, I forgot that it's times 4, so we're fine. And then store A1. So what this is going to hopefully do is turn on pin 2 and turn it back off. And then we're going to go put the stack back how we found it. I do have to move the ADI down below. Hello, Hardronics. Okay, let's go. So we were able to write it. Now let's go run the debugger and see how things... Ooh, that's not good. 42 nanoseconds is pretty good, but there's a problem. We have to acknowledge the interrupt, so we should really do that, I guess, down here. So I'm going to say LA, A5, and what we're going to want to load is we're going to want to load EXTI int FR is equal to 1 arrow 4. Why 1 arrow 4? Is that what that is? No, that's DP. DP. Why is... This is so sus. What is going on here? I guess we're gonna do it off of DPY. Maybe it's... I think that's it. Okay. And then in our assembly code, we should be able to load immediate, a 0, and 1 that, and we should be able to stay SW dot, or SW A0, 0, A5. I think that'll work. And so what we can do here is load A5 to be the address of intfr, which is in EXTI. And EXTI is this plus intfr. Oh, it looks like it's the first thing in there. Oh, wait, is it? That's DMA. EXTI. IntFR. So that's 048 12 16 20. Are we not allowed to do that? Oh, I'm not. Pound include rvo3usb.h.
Are you allowed to shift in the well, no, that should be just a constant though. So
yeah, my problem was I just didn't pound include the right thing.
Oh, okay. Yeah.
Okay. Oh. Okay. Whew. Uh-oh. That was weird. Wait. Anyway. Oh, yeah, now we're triggering off of channel 4. So it's only 40 nanoseconds, which is great. Okay. Yeah, so now we have our interrupt written in assembly. I should probably be taking notes about how all of this is going. So at 109, test interrupt in assembly. Oh, 109.00 complete. Continuing tests. Actually, yeah, if somebody, I wish I took more notes on when things are, because then YouTube can like chapterize it. So if anybody is already going to be watching this after the fact, if you want to go drop my Discord some of the time so I can go put them in the description, that would be awesome. Small microcontroller enough is just a small microcontroller is just powerful enough to run low speed 1.0, and it's actually 1.1. 1.0 is not what people use. USB 1.0 is janky. Actually, I don't even think USB low speed exists in USB 1.0 if I remember right. It's a really weird spec. Anyway, let's keep moving now. So here we can start putting code in between these two stores. Set debug pin high, set debug pin low. BSH, what is it? BSHR, BSHR, yeah. BSHR offset is going to be 16. Okay. Moving on. So let's go take another couple readings to try to understand what's happening. So we already know how c.nop and then the various things work. If we have an unaligned instruction, we should see how alignment works. SW, let's have li a2 0. Store a2 into the thing, and let's see how long that takes. And also, I'm curious what that assembly looks like. If it is truly being smart about compressed instructions and not, or if it's not smart. So let's take a look here. So we are at 82 nanoseconds now, and so that's with an extra store that's probably aligned and probably compressed. So let's take a peek. So it is store, store, store. So it is aligned and compressed. Okay. If we then instead, let's just validate that we know what we're doing. I'm going to write x0 into there, which cannot be compressed. And so we're going to go run that. Let's go see here. Okay. Oh, we should go configure this now. It will be 4. And let's only do for like 0.5 seconds. Okay. That didn't work. Did I select the wrong buffer? No, 04. Uh-oh. Something died.
Can you write to x0?
You can not write to x0. Writing to x0 does not write to x0. It just stays 0. It's not an error, but it's... Oh, I see. Ha ha ha. That's fair. That's interesting, though. I think that means that caused a crash.
Yeah, I didn't think it would cause a crash, but yeah.
Oh yeah, now it's definitely working.
That's weird. Yeah, I didn't think that should be a crash. I thought that should be a no-op or of some sort.
Yeah, I'm surprised as well, but I guess we've just discovered this, so let's see here, 82 nanoseconds. So this is hopefully an aligned full-sized write, or read, or write. It is aligned and it's a full-sized write. Okay, so that's also fine. But if we say c.nop here, then it should be slower. It should no longer be 82 nanoseconds, but my guess is that it's going to be more like 100 nanoseconds, 102 nanoseconds. So that really is it. So it looks like the instructions take longer if they're unaligned. But here's something I want to know. What about regular instructions if they're unaligned? So let's just say we say add I, c.add I, a2 0. And so this is going to be 2 instructions, and they are 82 nanoseconds. Okay. Now, what if I use the full-sized add I instruction? Wait, is that not allowed? Really? I guess it's not allowed. Okay, sure. Ooh, that's interesting. So this is an unaligned regular operation, and it's fast. So that's really weird. So only unaligned writes? Well, let's try an unaligned read. Let's see what happens if we do an let's just try reading. Let's see how long does reading take. We haven't done that yet. Load word A2, and then let's go just read back from, oh no, let's actually read from the port itself. Yes, Yes, this will be fun. We're going to actually start reading from the port. And so that's address 8. So, and that's called NDR. I believe NDR is the right thing, right? Give me a second. Just having to text my mother back. Okay, so NDR. Do unalign fulls? Okay, sorry, back to the chat. So Mike wants to know, do unalign full size instructions work? Yes. Yes, they do. They work 100% if you have the C-spec on. Otherwise, it would be really hard to like intermix your C and not C code and have it like all work out. Yeah. Anyway, so we're gonna load, and we're gonna load NDR into there. So let's go see how long this takes. That's so hard to believe. Wow, that's fast. That's really fast. Load word IOReg, and it's a is it aligned or unaligned? Load word IOReg. Oh, load word compressed IOReg. Okay, so load word IOReg. So it's actually CL load word IOReg. It doesn't really matter if it's compressed or not, and that's only 82 nanoseconds. There's actually two other things I want to find out with this. I want to know, what if I use the data right after that? So if I say add I, c.add I, actually I can do that, A2, and we're going to say 4. And so this is going to use the data immediately after fetching it. So let's see if that's what we would expect or something different. 102 nanoseconds. Well, I'll be darned. That's not that bad. That is then use data as c.add w. Well, that's really cool. So that means, so one of the things that I love thinking about all the time with all of my engineering is, how do I align my data so that my loads don't get used right afterwards, so that I can then have this extra cycle in between that it's not using it and I get a free cycle back. You don't have to think about that here. This doesn't do any of that. So it looks like that's just how it is. So now what I want to try is an unaligned. So c.nop. Oh, actually no, I want to do full-sized. So to do that, what is a full-sized reg that we can use? A full-sized reg would be, I guess, S1? No, wait, T. I can use T. So we should also back up T. T1. Four, 28, 32. Friday. No. No messing with the electronics. Okay. So let's try load word T0 and all of that. And let's see how long that takes. Oh, you can't do compressed, I know. Okay, let's give that a shot. Why is that not allowed? Oh, I blew my stack up. 32. So this is 82 nanoseconds, which is what I would expect. And that I believe is aligned. So that is load word C4. So that's an aligned one. So we should write that down. So load word irreg aligned. And that's 82 nanoseconds, right? Yes. Okay. So that's good. Next one, we're going to go see what happens if we forcibly unaligned it. C.nop. And so let's run that. Oh. And that's going to be 102 nanoseconds. So that's good that at least it's consistent. It looks like all memory operations are a little bit slower in that regard. Friday, come on. Friday. No bitey. Hey. Well, for some reason CatCam just died. Not that one. This one? There we go. Okay, CatCam is back. Hi Guardian, and I'm working on trying to add USB to a Tencent microcontroller. So at any rate, we have a load word that's aligned, and then our unaligned one is 104 nanoseconds. So that answers, I think, most of them. I think the one other thing I'm probably going to want to do is add let's see what happens when we access SRAM, because we're going to have to do that. We're going to need to read and write from RAM. Okay. uint32t test memory. And then over in this world, we can say, what is it? It's like global. Can you just do that? I think you can just do that. So I'm going to just load immediate A20xAAAAAAA, and then I'm going to go say SWA20 test memory. And then, we can do one extra one just to make sure that things are working well. We can say printf 08x test memory, and we're going to go see if that worked. This cat needs so much attention. One of the nice things, when people are over, is that they can give the cat attention while I'm live streaming. He normally isn't this bitey, but I think it's just that when he knows that there's stuff going on and he doesn't participate, he gets very needy and bitey. Very aggressive. I just wanted to verify, can people in the chat still talk on the stream?
I believe so.
Okay. Also, I'm not sure why it was scratchy earlier. It's better now. So, if I write LX, does that work?
Yeah, and it's midnight here, and I have a meeting at 8 a.m. So, yeah, I think I'm gonna have to get off.
Okay.
This was fun.
Well, neat. Glad you could drop by. How does this work? Oh, I think I have to do load immediate, A5A, say T0. Does that work? Load address. Yay! We can read and write to memory from assembly. Okay. So A4, we're gonna load that as test memory. And so test memory, A4, store word, blah, 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 A4, and we're gonna just give that a shot and see how long does that take. Clean all monitor. That's not good.
There was an error.
Where? Oh, yeah, here. Did Friday knock something out when he was back there? Oh, I think he might have. It doesn't look like it's knocked out. Uh-oh. Well, that's not good.
You got the same error again.
I know, I'm not sure why though. Like, what's going on that's causing this? If I write to the wrong place... Oh, maybe I'm writing... No. Oh, I am. A4 is the test memory. What's going on there is I'm blowing up the SWIO pin, so it's not able to be programmed, which is fair. Okay. (82 nanoseconds still. Well, that's pretty cool. So store word to SRAM is also fast.
What if you do multiple, like one after another?
That is a spectacular question. Let's have two variables. Test memory, and we'll actually define this as test memory 2. Okay, so we have test memory, and wait a minute. Oh, yeah, down here. This is the actual test. And we're gonna load 4. So, okay. 124 nanoseconds. Is that what we expect? Let's go look at the chart and see. 124 nanoseconds. 2x. See if I can entice the cat over here. I know you can't see it, but he's getting enticed. Whatever. We'll see if he comes or not. So 2x the store word is 124 nanoseconds. I think that's correct, right?
Wait, isn't that 2 more cycles instead of just 1?
It should be 2, right? All C.SWs are 2 cycles, not 1, correct?
Ah, yes. No, I was reading this wrong. You're right.
Okay, well that's pretty cool. What happens if we do a load word and then a store word? That's like the most hideous of any of them. What's wrong? What's wrong, Friday? Is that really 124 as well? That's pretty darn impressive. So it means that basically everything on this processor, if you're not running from SRAM, it takes... Wait, did we figure out what 2 full-sized adds were? Add I, A2, A2, AA. Wait, why is that wrong? Okay. Oh, nope. I didn't mean to click it twice. 104 nanoseconds. Yeah, that's really fast.
I'm curious, what about a just a unconditional branch? Or I guess a jump.
Oh yeah, we're gonna have to know that too. Add well, hold on, I want to find out, are these aligned or unaligned? These are unaligned, okay. I actually would expect aligned ones to be faster. They are not. Let's make sure that they are actually yeah, they're aligned. Okay. Okay. Sure. Yeah, that's a good idea, Mossler. Let's figure out how long conditional branches take. What's a good test for this? Let's say C dot BRNZ, is that what it is? A2 skip. skip. Okay. Nop. 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 Oh no, it's not BRNZ. I have forgotten my opcodes. Oh, what is it? It's something.
Is it BNEZ?
Is it like BRNEZ?
I think it's just C.BNEZ.
BNEZ. Oh, right there. Duh. C.BNEZ. Okay. 124 nanoseconds. That's a lot longer than I thought it would be. Let's just delete all of these just in case something weird is happening. Dang it, I did not mean to click that. 124, so it's the same no matter what. That's surprising. But I guess we'll record it. C.BNEZ branch taken. And that's 124 nanoseconds. That's really slow. Oh well. Oh, maybe there's something clever going on with the flash and caching. Well, not caching, but snooping? Because that's... Well, let's see what happens if we don't take it. Branch... what is the other one? Branch EQZ. BEQZ. EQZ. "60 nanoseconds." Wow. What? That's insane. That's like a one cycle overhead comparison. Wow. Okay, sure. Branch not taken. 61 nanoseconds.
Interesting.
Wow.
Very interesting.
So then I wonder what an unconditional jump is. So how do you do an unconditional jump with?
There's C.JR, which jumps to an address in a register.
I see J.
Oh, C.J.
Is that, I wonder if that does what I think it does, or if it's something weird. I guess we'll see.
Control transfer.
C.J skip.
And added.
Let us check.
Just an offset. Easy enough.
124 nanoseconds. I think the answer is this might be a fairly straightforward processor. C.J is 124 nanoseconds. Now let's just try to mess it up. Nop, 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 nop. Okay, let's just see what happens if we do something wacky. $124. That looks spectacular. Oh, this is nice. Wow, that's really cool. Okay, so it's like 2 clock cycles to take a branch, an extra clock cycle anytime you want to read or write to memory or IO, and then it's just 1 clock per instruction past that. I'm sure that there's other instructions that we'll need, but for right now, I think this list pretty much hits it. That's pretty fun. I think we've done pretty good here. Got a pretty good list together. Okay. Got a pretty good list together here. Starting right, NOP sled. Well, it's not really a NOP sled. It's a synchro sled. It's not really a sled either. Synchronizing code? Okay, so the sync code is going to... Oh, what we should also look at here is how long was this? Okay, so like by this time we actually get into the interrupt, it's like 861 nanoseconds later. That's so slow. But it doesn't really matter. Like, it's okay if it takes us a while to get going. That's fine. Whatever. So A0, A1, A2, A3, A4, A5, T0, T1. I'm going to just copy and paste the registers in because I never ever can remember what they are. It's S0, S1. S0, S1, A0, A1, A2, A3, A4, A5. And then RISC v registers. Which ones do we have access to? Oh, good grief. I don't know how. Is it A5? I guess it's just these. These are what we have access to. Zero RA SP GP TP, not that we're going to use those, T0 T1 T2, and then the compressed ones are S0 S1 or A0 A1 A2 A3 A4 and A5. Okay, so what I was talking about earlier is we need a mechanism to identify when an event happened. Actually, first of all, we need a way to identify if we are inside of a single-ended SE0 situation, which is here. So every millisecond, the host is going to send us one of these things here, which is 2 USB clock cycles where both D plus and D minus are low. So it's not differential for that. We just have to detect those and do something smart. So I'm going to load A5 GPIO DBase, and I'm going to actually read the register with it. So A0 BSRH offset A5, and we're gonna go and A0, and what we're gonna do is we're gonna have to create a mask of the register, or sorry, of the pins that we care about. So over here we have wait, where did Friday go? Oh, Friday's just out of view. There he is. We're gonna have to create a mask out of DP and DM, and it's gonna be dmask. So USB dmask is going to be 1 USB DM or 1 USB. I know you want attention, Friday, but I have to do this now. DP. Okay. And so our dmask, if that's 0, Friday. So we're gonna, Friday, stop. We want to do something down here, which is going to be handle, what is the name of that? USB in a nutshell. They're SOFs in full speed, high speed, and super speed, but there's a different name for them in low speed. Let's see here, SOF. It's on the next one. Nope, it's on the next one. The SOF packet is sent, right, but not for low speed. SE0. Oh, I'm not really sure we could. SE0 marker. Okay. And I guess here we're just gonna do something stupid. Exit interrupt. Or interrupt complete. I'm just gonna do that. Oh yeah, USB in a nutshell is amazing. I really should probably save this for when it inevitably goes down. And who knows if archive.org is going to still be around in a year. So, yeah. It's a pretty neat website. It just covers everything you really need to know about USB in a very short site. Anyway, yeah, so we can just kind of do that. And we could actually do one better. We could... Well, there's other reasons. Well, okay, well, let's just... What's that thing again? C.BEQZ. C.BEQZ. EQZ A0, comma, and then it's handle SE0 marker. So there we go, handle SE0 marker. And in here we want to do smart stuff with the 1ms tick. And so what that lets us do is we would be able to then make our local oscillator match the real oscillator, like the host oscillator. So we can synchronize our relatively bad clock to your computer's clock. So that's a pretty powerful thing.
How bad is the clock realistically? Because low-speed devices are allowed 1.5% plus minus leeway.
It's actually, so I did a couple tests, but and actually let's just do that right now. Oh no, register map. I've missed. It's pretty good, but it's not great. I done goofed. What did I goof? What did I mess up? I broke something. I'm gonna delete our test code for right now because I think we have a pretty good handle on it.
You're getting an error when programming.
Oh yeah, well it's because I'm writing to the bus port.
Ah, okay.
Let's just. Oh, and it's load word. Okay, let's try this. But unfortunately, anytime that happens, we have to like totally unpower everything. Oh, well that's ruined. Ugh. Okay. Did I still break it? I still broke it. What did I do to break it? let's not do that either. Because if you drive the debug pin high, or the debugger / programmer pin high, it's gonna stop you from being able to program it. Okay, let's hope I didn't break this. I still broke it. What am I doing wrong? I am super bricking this part. Soft bricking, not terribly bricking. I'm not actually sure what's going on. Why is this causing the part to go sideways? Oh, it's working now. So 994 milliseconds on something that should be 1 second. So 1000 minus 994. So it's 0.6%. Is how accurate this particular part is at this particular temperature under these particular situations or conditions. I mean, I don't know if that's good or bad, but it is within what is technically spec. But there's no reason not to. Yes, Mark, I can afford to buy a new one if I've bricked it. But no, actually, one of the nice things about the part is if you're not giving it power externally, I did add one of the features which I kind of like copied bits and pieces from the other one, which is -U, which is it super resets the part and super erases all of the flash. So it tries to unbrick it. So -U for unbrick. That does seem to actually... I've yet to have a part where I've bricked it so bad I can't do -U to unbrick. Anyway. Moving on. Oh, by the way, Mark, if you want some of these dev boards, let me know. I have a bunch more for you and your friends if you guys are interested. More tool chains. Yeah, need the unbrick flag. Yes, that would be very good. Anyway, so we have an SE0 marker. What I do want to do is I want to try load immediate A0, and what is the debug pin again? It's 2. Load immediate A1 16 plus 2. So hopefully now we can see how far in it is when... Well, that's not good. These should be valid data, and so we should be seeing output here on the yellow line. But if we comment this out, do we see output on the yellow line? We do. That's not good. That's not good at all. So if we and I A0 USB dmask, which should be 1 arrow 3 or 1 arrow 2. Can we not? Why is that not right? This should only skip the code, like if and only if. Wait, what in the world? Oh, let me delete some of this. I don't think we need this anymore. Do we? Yeah, no, we're good. We can just delete all this now. I want to detect the situation where both lines are low, and if they're both low, so if the ANDed mask is equal to 0, then NDR offset. Okay, there we go. That should be right. Mark says, I got a $50,000 thermal camera that worked throughout, and I had a scare because I pricked the controller. My home network gave it an IPv6 address that I didn't know what to do with. Oh, man. That's rough. I don't know. That's one thing. Mark and I have never seen eye to eye on IPv6. I hate IPv6. Mosseler, I thought you were an IPv6 person. Have you also given up on it?
I never believed in it.
Oh. Anyway, so what we actually have is the interrupt happens here. As that edge falls, we do a bunch of our slow stuff. It's fine if all of this is slow. Then here is where we actually start doing work again. But what we can do is we can wait until the edge, and then we can fall again. And I don't know if I want to do that in a loop. Sure. Let's just try it in a loop and see how that goes. Now that we know that loops are not great, but they're also not that bad.
Quick question, and
Shoot.
You may have done this earlier and I just didn't notice. Did you try outputting immediately at the top of your interrupt routine before you do any of those store words, just to see how fast it actually is?
Oh, that's a really cool idea. Well, we still have to do 3 things. We have to store A5 and we have to store A0. Or we have to store the... We still have to do some stuff. Like, do you mean that it would be convenient from the point of view of you spend less time interrupted when, if it's just an SE0 marker, you don't spend very long interrupted? Or something else?
Well, in general, you could store just one register, read the data if you need to read quickly, and then do all of the rest of the setup.
Sure, let's optimize it.
I'm just curious if that gets you more in line with a good delay.
Oh, I see what you're saying. Well, let's do... So what the idea here is, well, I mean, it's not going to draw, well, actually, yeah, we can do something smart there. So you're curious, like right here. So something like that, is that what you're talking about, Mosseler?
I guess, yeah.
The chances of this working and not crashing the processor are basic. Oh, maybe it worked. Oh, it did not work. Well, it sort of worked. Let's see what it actually is here. 16 plus 2. Let's actually do it the right way. It's still not great. That's surprisingly long. 444 nanoseconds. I mean, it's still in the first bit slice, but that's... Ooh.
That's like 20 cycles. What's it doing?
I'm not sure. I think, yeah, I am disabling HPE. Ooh. For the sake of writing it down, let's just try it with HPE on. $589. So it is slower. Okay, let's write that out. Jitter or interrupt reception test without HPE 444 nanoseconds, with HPE, what was it, 589. And actually there's going to be some variance, so that's not 100% fair. .602, yeah, but it's all going to be really close. It should be like about 1 cycle of jitter. Yeah. 582. Yeah. Okay, well that was fun. I don't know if I want to optimize it that heavily. Yeah, let's unoptimize it a little bit again. And by optimize, this is only, well, okay, I'm just going to get all the registers we could ever use. Okay, so now what we're going to do is... what is the interrupt vector free table free interrupt? Interrupt vector table free interrupt. Section 3.5 of the manual.
I think Sam may have gotten that wrong. There is no 3.5.
Oh, 3.49. Okay. I don't know what he's... I have no idea. Is it... Mike, this is the CH32V003. So CH32V003. Anyway. So what we've done is we've read in that that thing. And so what we can do now is, so if we've gotten here, it's a data packet. So it's not a single-ended 0. And sync loop. And what I'm going to do here is load word A0 in DR blah blah blah. And I'm going to go XOR A1 A2. Ooh, we need to and I. On A1 C dot and I A1 comma USB dmask. Then we can XOR A1 and A2. Is that a thing? Is there a compressed XOR?
Yep, C.XOR.
Destination source. I guess that's, yeah, okay, sure, let's do it. A1, A0. And we're going to branch if they are equal to 0 to sync loop. Okay, let's see if the chip blows up. Oh, also, no, we don't want to do it this way. We do want to have it unwound because we also want to handle a timeout. We don't want to... Yeah, we want to handle timeout too. Well, let's just see what this does anyway, because I'm honestly curious. So, oh yeah, that is awesome. So this is only happening when there's data, which is what I want. Wow, that's all kind of dumb. That happened at a totally random time, and that happens at a totally random time. So something's wrong with this. Is it branch not equal to 0? What? Oh, A1. Okay, so branch EQ. Ah, that's what I want to see. So now you can see it happens right after the edge, after, so it's 242 nanoseconds later. That's a while, but let's see how reliable it is. So 242, 150, 243, 273, 241. Okay, let's just say 273 minus 150, so 123 nanoseconds of variance. That's not great. That's like 4 cycles. Oh wait, that makes sense. It's like 4 or 5 cycles. Duh, because this loop takes 1, 2, 3, 4, 5, 6 cycles. Okay, let's just try it. Let's roll this or unroll this and see how it goes.
So I found what Sam was talking about. There are 2 channels of interrupts that you can use that skip going through the vector table, so they might be faster.
It really doesn't matter. I think that we're fine. As long as we can detect an SE0 event and we come in with a little bit of time in the front end of a sync word, it's fine. I guess it's annoying because it means that the SE0 happens every millisecond, so that's like code that you're stealing away from the user. But I think that's an optimization. That's not, or that's an optimization for later, or something offline, like something that's not going to be done on the stream. Like I want to try to do this on the stream. Friday. Stop. Friday. No bites. No bites. Stop. No. I just realized, is there a way in a macro assembler to like have several things all on the same line? Can I do this? No. What's wrong, Friday? I know that you want attention, but I'm busy right now. USB won't write itself. Actually, how do I, let me Google that. GCC assembler multiple statements on one line. A semicolon for separators. Let's give it a shot. Oh wait, no, that's the wrong thing. We want that to be all separate out. Here though, so I think this is 1, 2, 3, 4, 5 in 5 clocks per thing. Oh, Friday. So let's see, how many clocks would one USB time be? So one USB time is 40, or 48 divided by 1.5 is 32. 32 divided by 1, 2, 3, 4, 5 is 6.4. So if we do 5, 6. Oh no, we don't need 6. I think 5 is enough. Let's try this anyway. Optimization. I don't think we need this one. Okay, let's take a gander. So this looks rather nice. So let's see here. So that's 236 nanoseconds. 226 nanoseconds. 266. 241. So this is nice and stable. 240. 227. So this looks like this is some good legs on it. I think that this is a reasonable way to go. So what this is going to let us do is we're going to be able to start here and sample here. Uh-oh. I know, Friday. The fire alarm just went off. I know. Sorry, Friday. I guess it would be irresponsible to just stay put, even though I do have access to the back deck. I can just get out at a moment's notice. Yeah, I think I should probably stop streaming right now, although I probably will be back. I'm going to do this and just take Friday and exit. See you guys.